Hello again, everybody. Welcome back. So in the last video, we defined what a random variable is and the difference between a discrete random variable and continuous random variable, and how different they are. So right now, I'm just going to focus on discrete random variables for this video. Because they're dealing with their probability distributions are easier to work with. So let's just say that if x is a discrete random variable, and we're going to assume that in this case there are only finitely many values. So x1 through xn are just numbers, and these are all the possibilities that x can be. Then we can talk about the probability that x is equal to x1, the probability that x is equal to x2, and so on. And in fact, we'll let p sub I be the probability that x equals x sub I, right? So these p's represent all the corresponding probabilities. Now notice that because they are probabilities, they're numbers between 0 and 1, and the sum of all these has to equal 1, because x has to equal one of these, right? And all these cases, you take any two of these outcomes. The x can't be equal to, let's say, x can't be equal to x sub 2 and x sub 3 at the same time, right? So the probability that x is equal to either to x1 or x2 or x3, or all the way up to xn, probability of that x is exactly one of these is 100%, or just 1, right? So that's why the sum of these probabilities has to equal 1. And what I've done here is I put I have two columns where we have all the possible values of x and the probabilities that x is equal to those values. And this is what we call a discrete probability distribution. Okay. Now we did this in our first example, right? And we had where we were tossing a coin 3 times, and x was the number of heads, and we we did everything except write a table, right? We could make a table right here. Here's x, and here's p of x. Now p of x is just the notation for the probability that x is equal to whatever x is. So basically, these are the possible values of x in this case, and we said the probabilities. For the corresponding probabilities, we said were 1/8, 3/8, 3/8, and 1/8. And notice that if you add up all these numbers, you get 1. Okay, so that was this is basically the probability distribution associated with this random variable x. Now. And the thing is, you can actually make up any probability distribution you want. You can just pick put whatever numbers you want over here, and then put whatever numbers you want over here, as long as these numbers add up to 1, and that these are between 0 and 1. Now, just like we talked about the mean and the data set, we can talk about the mean of a random variable. We define the mean of a random variable x to be the sum of all the products of x sub I times p sub I. That is we take all these numbers, and we take these pairs, multiply them together, and add them up. So this would be x1 times p1 plus x2 times p2 plus xn times pn, and we add them all up, and we say that this is the mean of x. Okay. Now, what does that mean? Well, basically, that's a theoretical value. Okay, it's very more likely than not that x will never be equal to its mean, and we'll see an example in a moment. But what the theoretically is that you could see that if you were to run this experiment thousands of times. Then we can, and then just take the average of x over that 1,000 or whatever, how many trials you have, then this would be on average, this would be the average value of x. Okay. Now we also have something called a standard deviation of x, because this is technically a distribution, so we can define the standard deviation of x and the variance of x to be this way. We basically it's very similar when we're talking about to the variance and standard deviation of a data set. We just take all the possible values of xi, take the xi, subtract the mean, square that difference, and in this case we're going to multiply it by the probability, corresponding probability piece of y. Okay, so that is the variance, and then the standard deviation is the square root of the variance. All right. So we're not going to be doing a whole lot with this, at least for not distributions. At least not for discrete random variables. What we will do will be doing a few examples with this. So if we go back to our first example, what was going to be the mean of this one? Well, the mean of this we would see would be mu, would be 0 times 1/8 plus 1 times 3/8 plus 2 times 3/8 plus 3 times 1/8. Now if we add this all up, it turns out to be 1.5. Okay, because you get 3 plus 6 plus 3, that's 12/8, which reduces to 1.5. Now, what does that mean? Well, we know obviously x is never going to be equal to 1.5, but let's say if we were to do this experiment 1,000 times, what would be the total number of heads if we added all on average? What would be the if we added up all the x's from there? What would we get? Well, it would be if we were to sum up all the x's, this would be 1.5 times 1,000, which would be 1,500. Now, remember, why does this work? Well, remember we're tossing a coin 3 times. Okay, so if we repeat this experiment 1,000 times, that really basically adds up to 3,000 coin tosses. And because the coin is fair, we could expect the number of heads to be half of that, which is precisely 1,500. Okay, so it does make some sense, right, for expectation. Now, what would be the variance? Let's compute the variance of this, just because we kind of have to. Okay, so the mean is 1.5. So what we do this, we would take again, x goes from 0 to 3, so we'd have 0 minus 1.5 squared times 1/8 plus 1 minus 1.5 squared times 3/8 plus 2 minus 1.5 squared times 3/8 plus 3 minus 1.5 squared times 1/8. Okay, there, so you can see that. And if we compute all of this, and I did that ahead of time, I think this turns out to be 0.75, approximately 0.75, and then the standard deviation is a square root of 0.75, which is 0.866 about. Okay, so this would be the standard deviation. This would be the variance. All right. Okay. Let's do one more example. Example 3. Notice we can't do this with example 2 because example 2 was a continuous random variable. So let's look at example 3. Here we have a small town that consists of 300 households, and let's say we want to we have the data about how many TVs they have. Okay, and we're going to pretend that each household has at most 3 TVs. Okay, so we say that 29 have no TVs, 57 has 1, 109 have 2, and 105 have 3. So we pick a household at random, and in this case we're going to let X be the number of TVs in that household. Alright, well let's first get a probability distribution. Okay, once again X can be only 0, 1, 2, or 3. These are all the possible values of X, right? So if we make, here's X, and here's P of X. So here's 0, 1, 2, 3. Okay, so what would be the probability that our household has none? Well, there are only 29 of them out of 300, right? So the probability would be 29 over 300. The probability that X equals 1, that would be 57 out of 300. The probability that X is 2, that there are exactly 2 TV sets, that would be 109 over 300. And the probability that X is 3, that would be 105 out of 300. Okay. So that would be, this would be the probability distribution, and the mean would be, once again, here's would be 0 times 29 over 300 plus 1 times 57 over 300 plus 2 times 109 over 300 plus 3 times 105 over 300. Okay. And what I did, when we compute this, I get this turns out to be 590 over 300, which is approximately 1.97, okay, is your mean in this case. And then the variance would be computed this way: 0 minus 1.97 squared times this probability plus 1 minus 1.97 squared times this probability plus 2 minus 1.97 squared times 109 or 300 plus 3 minus 1.97 squared times the probability, which is 105 over 300. And if you compute this out to get that this is approximately 0.9256, and so the standard, that's the variance, and the standard deviation would be the square root of this, which is approximately 0.962. Okay. And again, what this means is the average value, the theoretical average value of this would be 1.97. Okay. All right. So we'll have one more video about expected value, and that will be the next video. See you then.